Okay, driving force. Driving force is the thing that makes something happen. Okay? And the reason why chemical reactions happen is because of the fact that full energy levels are very low energy. And once something gets to very low energy, it tends to stay there. I don't put the bowling ball on the top shelf because it's going to fall. But once I put a bowling ball in a hole in the ground, it's going to tend to stay there, where it's reached its lowest energy. Okay? So, which elements have full energy levels? The noble gases. Noble gases have full energy levels, so looking like a noble gas is very low energy. And once you get there, you stay there. So if you're going to try to figure out how an atom's going to react, here's the rule that chemists use. Atoms behave in a way to achieve noble gas electron configuration. They do what it takes so they can look like a noble gas. Can't be the king, but you can look like the king. Now, their electrons are arranged like noble gases, but they aren't the noble gases because noble gas looks that way without a charge. In order for them to look like noble gases, they're going to have to change the number of electrons, which means they're going to have a charge. Okay? So this is the underlying reason for why chemicals behave the way they do. They want to look like noble gases, which we're going to use that as the reason, but the real reason is because noble gases are really low energy. Okay? So for second ionization energy, the energy to remove the second electron. How could they look like noble gases? How could they look full? Well, if the thing looks like a noble gas after you take the second electron off, you're going to get a lower number than you expected for the ionization energy. That means it's easy to form. Ionization energy is the energy you have to put into an atom so it can take the electron off. It's lower than expected for the ones that look like noble gases when they lose the second electron. So which atoms are we talking about? Which atoms will look like noble gases when they lose their second electron? Well, the ones with 2 more electrons than noble gases. That seems pretty reasonable, right? So if they're going to have 2 more, that means there'll be 1, 2, the alkaline earth metals, the S2s. So when they react, when you threw that calcium into water, it made a 2+ ion. Because it reacted with the water, right? The way it reacted was, it gave its electrons to water. Here, water, take my electrons. I don't want them. I want to look like a noble gas. That should say alkaline earth metals. Sorry about that. Spell check won't catch that. Alkaline earth metals. So alkaline earth metals always form a 2+ ion. What about alkali metals? How could alkali metals look like a noble gas? Just lose one electron, right? So the alkali metals, group 1A, loses one electron. It looks like the noble gas before it. So those ones that are after the noble gas are the ones that come off. When you write the noble gas configuration, those come off. The S's and the P's. So third ionization energies, which ones are going to have low third ionization energies? Not the D1. So which ones are going to be easier to lose 3 electrons from the highest energy level? Well, the ones that have 3 electrons in their highest energy level. Does that make sense? So the ones that have 3 electrons would be 1, 2, 3. S2P1, right? The boron family. The boron family, those metals form 3+ ions. So I would expect aluminum to have a low third ionization energy. But that means low compared to other third ionization energies. That third ionization energy still has to be higher than the second. So compared to other atoms, it has a low third ionization energy. But second ionization energy is always bigger than the first. The third is always bigger than the second. The 91st is bigger than the 90th. It's harder to take off the 91st electron than it is to take the 90th electron. So back to those numbers we looked at quickly yesterday. There's this table. And you'll notice, once again, point out that it always gets bigger as you go to the right. That the third ionization energy is always bigger than the second. And the second is always bigger than the first. Works every single time. But they don't move around evenly. For helium, the difference between first and second is about a doubling. For lithium, it's over 10 times harder. Big jump. But the next one doesn't jump 10 times, it doesn't even double the next time. Whereas beryllium, the first one comes off fairly easy, the second one comes off fairly easily, but the third one takes a whole bunch of energy. Why? Well, lithium loses that first electron really easily. It looks like a noble gas. It actually lost the whole energy level. Right? Lost the whole energy level. So it lost a whole energy level. So it looks like helium, looks like a noble gas. It's happy. So when I go to get that second electron, I'm getting it from a big charge without any shielding. Because this looks like helium. Only it's got 3 protons instead of 2. So it should be harder to pull that electron away from 3 protons instead of 2. Make sense? Okay, so lithium's first one is easy, second one is hard. The second one is much harder, the third one's just harder. Okay, but if I look at beryllium, the first one is easy, the second one is easy, the third one is really hard. Why? Well, the first one is easy because I'm taking it out of the second energy level. The second one is easy because I'm taking it out of the second energy level. But then I look like helium. And when I go to get the third one, it looks like helium. It lost an energy level. Except now you're trying to take it away from 4 protons instead of 2 protons. It's going to be much harder. So these 3 right here, the big numbers on this chart, okay, those are all things that look like helium. Okay? But lithium looks like helium with an extra proton. Beryllium looks like helium with 2 extra protons. So that third one's going to be really hard to take away. Okay? And the same thing happens further down. Here's the place where the first ionization energy drops where you don't expect it to, but it does that here. And it does it here. That even the exception pattern follows the rules that when I have P4, taking the next one off is a little easier. Does that make sense? Okay. So that's how the different ionization energies compare to each other. So ionization energy in general increases as you go up and to the right. It increases when you go up because you've got less shieldings, so you can feel that nuclear charge more, less things in the way, fewer papers on the fridge. And it goes up when you go across because you've got more protons pulling that same energy level. Okay. So now we're going to try to figure out what pattern there is to the size of ions, which leads to a problem. We haven't talked much about ions. Okay? Ions are when atoms have a charge. And there's two possible charges, so there's two kinds of ions. Okay, the two kinds of ions have names. Positive ions are called cations. Or cations. It's not caution, there's no U. Cation. Cations are positive ions. So I need you to remember that cation means positive. Okay. And I said, okay, well, I can tell you that the plus sign, the T looks like a plus sign. That's a reminder. But actually, there's a way that works really, really well. I'm not a big fan of it, but it works really well. People tend to remember it. So here's how you remember it. Cations are positive. Positive. Cations. I couldn't think of anything positive to say about a cat, so. Okay. Cations are positive. How are you going to make a cation? You have to have more positive pieces than negative pieces. Right? So how's that going to work? Which one are you going to change? The positive piece or the negative piece? Or both? Only the negative piece can move around. So how are you going to make something positive? I need to get rid of some of those electrons. Now, cations are much smaller than the atom they come from. To give you a sense of why they're much smaller, let's look at lithium, sodium, and neon. Okay, in terms of size, lithium is going to be smaller than sodium because lithium's got one less energy level. So if sodium was this big, lithium would be that big. Okay? And neon compared to lithium, now we're talking about the same period, so it's about more protons. More protons pulls it closer. So neon is going to be smaller than lithium. That's what we talked about yesterday, right? Atomic size. It gets bigger as you go down, bigger as you go to the left. Okay. But now let's think about sodium with a charge. Okay. Well, Na is 1s2, 2s2, 2p2, or 2p6, 3s1, right? When it loses that electron, it loses the whole third energy level. So now this sodium plus looks like neon, but neon looks like neon with 10 protons. The sodium's got 11. So the sodium starts off bigger than neon, and by losing one electron, ends up smaller than neon. That one electron makes a big difference because that one electron is alone in the outer energy level. So that's why it's not just smaller. Oh, you lost an electron, you're smaller. No, you lost an electron, lost a whole energy level, so you're much smaller. Because you lose that whole outer energy level. Okay, when we started this unit, we said, here's the periodic table, how it's made, and then we started breaking up into things. The first thing we broke it into was metal, metalloid, and non-metal. And I talked about what metals were like, I talked about what non-metals were like, and then I said the metalloids had properties of both, and I couldn't really explain what I meant by properties of both. Kind of shiny, kind of brittle, that sort of conducts. Well, sort of conducts was the one we could talk about, but kind of shiny, kind of brittle, no. The real difference is right here. What makes something a metal is that it forms cations. Metals are losers. You get a metal when you win. The metals you have are losers. They lose electrons. That's what makes it a metal. When it reacts by losing electrons. Okay? And it's going to lose electrons until it looks like a noble gas. So the cations of representative elements, remember representative elements means group A's, or representative elements means the S and P's are filling. They're going to lose enough electrons so that they look like the noble gas before them. So metals are losers, and they lose enough to look like a noble gas, which is why alkaline metals make a 1+ ion, and alkaline earth metals make a 2+ ion. The boron family makes a 3+ ion, if they're metals. Okay. So, if I take that electron off, it's smaller, right? But I really need to compare it to the neon that was 10 electrons and 10 protons. Can you see why this Na plus is going to be smaller than Ne? Because they both have the same electrons, but this has 10 protons and that has 12, or 11. 11 is going to do a better job of pulling in than 10. More nuclear charge pulls it in more. More nuclear charge means more protons. So you lose an energy, which means you end up much smaller. Okay? Okay, so now we're going to write about the opposite of everything you just wrote. Okay, the first thing I said was cations are positive ions. The negative ions are called anions. And to remember that, it's a negative ion. That's not where the prefixes came from. They actually came from anode and cathode on a battery. The positive and negative ends of the battery is where those names actually came from. But a negative ion makes it easy to remember that they're called anions. So how do I make a negative ion? Okay, I got to have more negative pieces than positive pieces. And which ones can I move around? Can I move the positive pieces around? No, I can only move those negative electrons around. So anions form by gaining electrons. So anions are bigger than the atom they come from. Just a little bit bigger, not a lot bigger. Okay, if you go back and look and see what we said about cations, you should know what the next phrase is going to be. What did we say right after that? Cations are much smaller than we said. Metals form cations, so nonmetals form anions. Nonmetals always react by gaining electron. And now we can talk about what metalloids do, how they can be properties of both. Metalloids can sometimes gain electrons and sometimes lose electrons. That's how they can have the properties of both. If you put a metal with a metalloid, the metal is going to give its electron to the metalloid. You put a nonmetal with a metalloid, the nonmetal is going to take the electron from the metalloid. The metalloid can either take electrons or give them away. That's how it can have the properties of both. That's what properties of both was supposed to mean. Is that sometimes it loses, sometimes it gains, depending on what you put it with. And how many is it going to gain? What does it want to look like? Noble gas. So it's going to gain enough to look like a noble gas. Now, it's not going to be the noble gas because it's going to have the same number of electrons, but it's going to have a charge. That charge is going to make it behave differently than the noble gas. But it got to a place where it didn't want to change its electrons anymore. And again, it says representative elements. That's the A groups, or the S's and P's. The patterns don't work in the D's, so we don't try to use patterns to explain D's. So, what ion would bromine form? Well, it wants to look like a noble gas. It's going to gain one, look like krypton, so it's going to make, a 1 minus ion. With hiccups, oh no. Okay. What ion would nitrogen make? How could it look like a noble gas? Well, it would have to gain 1, 2, 3 electrons. Okay, so it would make a 3 minus ion. They gain enough electrons to look like a noble gas. So nonmetals gain until they look like a noble gas. Metals lose until they look like a noble gas. That's what's going to make reactions happen. So, here's this. When I add that electron, it gets bigger, but it's still smaller than neon. That the extra electron made that a little bit bigger. This would be F minus. Okay. So it got a little bit bigger because it's harder to hold in 10 electrons than it is 9 electrons. Okay. But with 9 protons, this is not going to do as good a job as neon. So it's going to look like neon, only be a little bit bigger. Okay. So the size difference isn't as dramatic for nonmetals as it is for metals, because metals lose the whole energy level. They make a big change. So, what is the configurations of ions? How are the electrons arranged in ions? They have noble gas electron configuration. Again, we're only talking about representative elements, the tall columns, because the patterns are easy to predict there. So sodium is 1s2, 2s2, 2p6, 3s1, or I could have written neon 3s1. Okay with that? So, is sodium a metal or a nonmetal? It's a metal, and we know metals are losers. So it's going to lose. How many is it going to lose? Well, enough to look like a noble gas. That means it just has to lose that last one. And it's 1s2, 2s2, 2p6, which is neon's electron configuration. And that's the reason why we want to use that shorthand, because it focuses on the ones we want to change. We're either going to fill them up or empty them out. That's why we want the noble gas electron configuration. So metals are losers, non-metals are gainer. They're going to lose enough to look like a noble gas. They're going to gain enough to look like a noble gas. Everybody okay with that? Hey. So now that we know how to make ions, let's talk about their sizes. So, group trend. You didn't graph this one, but this is what it looks like, if you had. What's the general trend? Increases. So further down a group, the higher the bigger the ionic size. Why? Well, they all look like noble gases, but they all look like the noble gas before them, right? So you got something that looks like neon and something that looks like krypton. The krypton is going to be bigger because it's got extra energy levels. Down a group, the reason down groups is energy levels. Got more energy levels. So if I'm asking compare top to bottom, it's going to be energy levels. And I drew pictures here. And you look at those pictures, it may look like I left off hydrogen. I didn't. I drew it to scale. Say, what do you mean you drew it to scale? Well, let's think about what H1 plus is. Hydrogen, what's its atomic number? Its atomic number is 1, so it's got 1 proton and 1 electron. How do you make a 1 plus ion? You take away an electron. What are you left with? Just a proton. So if I drew a dot on here, it would be too big compared to the other atoms. Because if an atom was this big, would you be able to see if a baseball field was that big, would you be able to see a baseball on it? Right? So a dot would be too big to show you where the proton's at. Okay? That's what makes hydrogen and acids really dangerous. We got a charge piece, and charges mean they can hang on to stuff, because opposites attract. And it's really small. It's just a proton, so it can get really close. And the closer you can get, the more it can hang on. And that's what makes acids dangerous, is that little H plus can get into little tiny places and tear stuff apart. Hook onto the negative of this chemical and tear that molecule apart. That's what it's doing. So H plus is really dangerous, which is why acids are dangerous, because it's a little tiny charge piece. So there's the group trend. As you go down a group, they get bigger because they all look like the noble gas before them, which means you've added energy levels still. You took off the energy level, but they still have, this is 0 energy levels is going to be smaller than 1, because lithium lost its first energy level, still has one, or second energy level, still has 1 left, right? Here's the period trend. So it's the trend. The trend is increase. No. The trend is as you go across, the nuclear charge increases, so they get smaller. If you look at the trend is smaller. Every one of these got smaller. Every one of those got smaller. It's just between these two spots that it did get smaller. This part goes down. The first half of the graph goes down. Downward. Second half of the graph goes downward. It's just there's this big jump in between. So what's going on that, because increased nuclear charge, they get smaller. And that works 7 out of the 8 times there. On your way, 6 of the 7 times you move across. Okay? There's only one place it doesn't work. Why doesn't it work there? Well, let's stop and think what they look like. Lithium has lost 1 electron. It looks like helium. Beryllium has lost 2 electrons. Started off with 4, lost 2. It looks like helium. Boron started off with 5, lost 3. It looks like helium. Carbon started off with 6, lost 4. It looks like helium. Nitrogen gained 3. It looks like neon. Oh. Well, that would be different. The reason why they're different sizes is because the nonmetals look like the noble gas after them, and the metals look like the noble gas before them. That the split happens when I'm talking about positive to negative. Does that make sense? So if I compare all the positives, the trend works. If I compare all the negatives, the trend works. I just can't compare the positives and negatives because there's an energy level change. Lithium has, when it loses its electrons, has 1 energy level left. Fluorine, when it gains electron, has 2 energy levels. Is that right? Reasonable thoughts? So it doesn't make sense to compare positives to negatives. Because it's comparing apples and oranges. I really want to compare the things that look like each other. So what I really want to compare is, here's a $10 word, isoelectronic ions. That's got to be a hard word to define. Isoelectronic? Nah, it's really easy. This is where knowing what your roots means get you along. The prefix iso means same. So isoelectronic, same electrons. Isoelectronic ions have the same number of electrons. There's going to be a whole bunch of things that look like neon after they've either gained or lost electrons. There's going to be a bunch of things that look like krypton after they've gained and lost electrons. That's the ones that make sense to compare. Here's a set of isoelectronic ions. Aluminum 3+, magnesium 2+, sodium 1+, neon. Well, technically that's not an ion, but it's isoelectronic. Fluoride, fluorine with a 1-, oxygen with a 2-, and nitrogen with a 3-. All of those have 10 electrons. Aluminum started off with 13, lost 3, it's at 10. Magnesium started off with 12, lost 2, it's at 10. Oxygen started off with 8, it gained 2, it's got 10. All these have the same electron configuration. All of them have noble gas configuration. So that's what we mean by isoelectronic. There's going to be a whole bunch of things that look like each other. But some are going to have charges, so they're not going to be the same thing. They're just going to look the same thing. If I put the crown on, it doesn't make me the king. So if I look at those in terms of size, that list of all those isoelectronics, Which one would be small? Well, it can't be because of electrons, because the electrons are all the same. So the difference has to be protons. The more protons, the more you pull. So the aluminum would be small, and the nitrogen one would be the biggest. Positive ions have more protons, so they're smaller. Negative ions have less protons, so they're bigger. So the more negative it gets, the bigger it gets. Because all of these have 10 electrons. But aluminum is pulling in 10 electrons with 13 protons. So I got 13 protons. And this is pulling it in with almost half as many. 7 protons. 7 protons is not going to pull in as good as 13. So when you're comparing ions, compare the ones that look like each other. Okay. Homework's on the book. Have a great afternoon.